Good afternoon, everybody. So I first would like to thank the organizers for the invitation. And in spite of me being an outsider of this community, at least I have some contact with the title of the conference as far as topology is concerned. But I'm pretty new in what respects to ferroelectricity or ferroic materials in general. So I would like to tell you about some work we did on some magnetic frustrated magnets and what we have observed there in some intermediate regime of magnetic fields. And on Tuesday, they scheduled another talk from me. And there I would like to be more informal and will tell you more what things I have done that could be related to multiferroics. So this was the main idea of my visit here, or my participation. So this is work we have done in La Plata in Argentina with my PhD student Osorio and my collaborators Rosales, Rossini and Sturla. And we are still working on these issues, trying to understand some more details. Please, you can ask questions during the presentation if you want. So essentially, well, I'm not sure if I'm going to cover all these points, but the idea would be to go through a bit of history. But since here you are all experts, I will be pretty fast, and then I will just flash some experimental results where skyrmions started to be observed, and how these experimental observations were understood using ferromagnetic models with Yoloshinsky-Moriya interactions in most of the cases. And then I will move to what we have done, which is to see what happens when you have antiferromagnetic exchange with the Yoloshinsky-Moriya interactions and the magnetic field. And I will show you some, what we call at some point, there should be quotation marks there, antiferromagnetic skyrmion, lattice. I will explain why. But this is something different from the skyrmion lattices that you observe in ferromagnetic systems. Okay, then I will show the phase diagram and the low energy effective field theory description, which in principle would be a working tool for analyzing coupling to the lattice and, for example, with the charge degrees of freedom to see whether some polarization could show up. Okay. Okay, so this is a very brief and fast overview. So skyrmions appeared first in the paper by Skyrmer. Well, they were not called skyrmions at the time. But I will more interested in what is a two-dimensional version of this original skyrmions, and these have been studied by Belavin and Polyakov already in '75, studying this nonlinear sigma model. And here maybe I will just clarify the notation because I'm mixing. So normally I have used this kind of normalization in the notes, so sorry for the mixture. So n with the s square here, this is just a exchange Hamiltonian for a ferromagnet. And if you go to the continuum limit, you get the nonlinear sigma model, which looks like a Gaussian model, but you have this constraint. So this is why it is nonlinear field theory. And what these guys have shown is that if in the case of a theory where your order parameter is satisfies this constraint, so it's kind of S2 variable. So these guys will be a function of the position, but for all positions there are variables that have fixed modulus equal to 1. And in that case, you have a topological charge that characterizes these mappings. So in this case, what you have to do, this comes later, but let me just draw something. So you can take R2 and compactify it into the sphere. So these variables n are mappings from S2 to S2, and this gives rise, probably I'm going into too much details for you, but I just want to make it a point later about the difference with the triangular case. So essentially, this is why you have this topological charge, because the second homotopy group of S2 is non-trivial. And of course, in the case of a pure ferromagnet, these skyrmions are metastable states, but we will see more complicated models where these guys could appear. In particular, if you have Dialoshinsky-Morilla interactions that could be present if inversion symmetry is broken, and then these excitations or quasi-particles, defects, however you want to call them, could be part of the ground state. Okay, so some pictures. So what I said is, if you compactify that 2 to S2, then you have maps from S2 to S2, and this pi 2 of S2 is the set of integers, and this is what gives the charge, the origin of the charge. The other thing I would like to use, so we know that pi 2 of S2, well, I should be, this is Z, but we also know that pi 2 of S2 is trivial, okay? So there are no vortices here. And this will change when we move to the antiferromagnetic triangular case. So essentially, okay, this is typical topology argument. So you have these charged states, which look like this or like that, but they are topologically stable. And so I will skip this because I assume that you all know about this. And this is some history, at least from my point of view, how I started to be interested in the subject, which is that what happens in chiral magnets. So, okay, of course, I didn't start from this paper, but this was one of the, I think, the first paper where they predicted a skyrmion lattice in a two-dimensional chiral magnet already in 1989. And to my knowledge, it was in 2009 where they first observed these states in, well, first in a three-dimensional material with this MNSI, where you see each of these bubbles here is a skyrmion. And okay, let me just move to a two-dimensional system, which was studied a little bit later, which is this compound here. And here you see in a, this is a phase diagram, magnetic field versus temperature, and you see in this very large region this skyrmion lattice state showing up. And okay, these are theoretical studies using a minimal model that I will show you in the next slide that has exchange interactions, Dialoshinsky-Morilla interactions, and essentially with this you can cook up these kind of phase diagrams. Okay, after these papers there appear many papers showing skyrmion lattice states. Also more recently there are some other more complicated systems where skyrmion lattices appear with skyrmions with higher charge. So in these cases, all skyrmions have charge 1. But there are some situations that are not yet understood from the theoretical point of view, but where skyrmions can crystallize, but now they have charge 2. This is, I haven't seen higher charges, but at least charge 2 skyrmions, or they are also called biskyrmions, appeared recently in many papers. Okay, so the theory, well, I will, this is very trivial. So ferromagnetic and antiferromagnetic is, well, at least for classical spins, let me focus now on classical spins, it's very easy to understand, but already at the classical level, if you have easing spins, you get this frustration typical situation. Of course, if you have Heisenberg, or let's say vectors instead of Ising-like spins, then you can relieve frustration and find a ground state, which will be these 120-degree states. But what happens now if we stay on this side? So we stay on the bipartite systems, and we add this Dialoshinsky-Morilla interaction. So this is for example, when you have D going out of the plane, so you will get some kind of a spiral with some rotation sense depending on the sign of D. But this is a very trivial case. And the interesting thing is that when you combine in 2 dimensions J and this the Aloszynski-Moriya term and the magnetic field, you can get these exotic states. And this is, okay, each of these bubbles is what I would call a skyrmion of charge 1. Okay, so this was studied by Nagaosa and collaborators, among others. And this is one of the papers where they looked at microscopic Hamiltonian. So this is just exchange in a cubic lattice, so S and the coupled to the 3 neighbors in the cubic lattice. This is the Aloszynski-Moriya interaction, which have the the vectors pointing in the direction of the bonds, and then some extra terms that are needed to stabilize these skyrmion lattice faces. And essentially, the main result from the theoretical and the continuum limit from the theoretical point of view is that these faces are obtained if you analyze this continuum model. So this first term is first term I have shown you from Belavin and Poliakov, which corresponds to the nonlinear sigma model term. Then you get this term, at least for this cubic symmetry, when you go to the continuum limit. So this the Aloszynski-Moriya term goes in the continuum to this first derivative term, which provides the way to get some skyrmionic phases, helical and skyrmions and so on, and the magnetic field, which seems to be crucial also to stabilize these skyrmion lattices. Okay, so this is for what is known for bipartite lattices. So this is the typical phases you find. And so our question was, what happens if one moves to some more complicated models? So our first attempt was to look at the hexagonal lattice, or honeycomb, should I say, honeycomb lattice in 2D, and we didn't find anything different from the square lattice because, well, for obvious reasons. Well, not so obvious at the time for me, but it's a bipartite lattice, so nothing new was observed at the time. So we moved to the antiferromagnetic triangular lattice, which from the topological point of view has an important difference. So in the case of the triangular case, if you study the simplest 2-dimensional Heisenberg antiferromagnet, this was studied already in '84 by Kawamura and Miyashita, where they have observed that if you look at the number, okay, so maybe I should go slower. The first thing you have to observe, the triangular lattice case, is that now your effective action or your phase space will be described not by an S2 vector, but by a matrix, okay, an SO3 matrix. And having noticed that now S2 is no longer there, but SO3, and this is related to the structure of the ground state. So in the bipartite lattices here, either you have this or this. Here, what you have in the ground state is something like a 120-degree structure, and this has to be characterized with some other variable, which is an SO3 matrix, and this is what gives rise to these Z2 vortices. So essentially now these things here change to the following. So pi 2 of SO3 is trivial now, so there should be no skyrmions, but on the other hand, pi 1 of SO3 is Z2, okay? So maybe I forgot to mention that this is what gives rise to skyrmions, but I think I have said that, and you should know. Okay, so essentially in this paper, this issue was studied for the first time, and what they have observed is that if you count the number of vortices in a way that I will describe if I have the time, but there is some way to count, to look at these are Monte Carlo simulations, so you can analyze your equilibrium states at a given temperature and see whether you have these topological excitations or not. And what they have observed is that the number of vortices as a function of temperature shows a very interesting change around 0.3 for the values of couplings, and this was understood as a kind of Koster-Rithaulus transition, where these Z2 vortices are those who proliferate above the critical temperature. Of course, this is not exactly Koster-Rithaulus, because here both phases on top of Tc and below Tc, above and below Tc, both are massive phases, but there is a change in the regime. They characterize this change using some vorticity function that I may describe, some variable that distinguishes the two phases. And okay, so this was in '84, but Kawamura is still working on these issues, and he has a list of materials where these kind of transitions could be observed. Okay, so as I said, then in the triangular lattice for the antiferromagnetic case, we need more structure to describe the phase space, as already noticed by Kawamura Miyashita. Later on, Dombra and Reed in 1989, they studied the low energy effective action for this antiferromagnet, and they described this as one would have expected, but they constructed explicitly the SO3 based nonlinear sigma model. So instead of the nonlinear sigma model with the vector n, now you have a nonlinear sigma model with some field, which is an SO3 matrix. Okay, matrix. Okay, so as I said, pi 2 is trivial, so there should be no skyrmions, but one should be able to observe these these vortices. Okay. And okay, these are some pictures reproduced from the original paper by Kawamura Miyashita, where if you look at these triangles, when you have this singularity here, you can see that some twisting around the singularity is being there. Okay, I didn't say why there is a singularity, and I will not have the time, but I will be here for a few more days. So if someone is interested, I will be very happy to discuss more about this. But believe me that there are structures here of this SO3 parameter that have these defects, and these are two situations. So here, for example, you see in this case, which in fact turned out to be according to these guys, turned out to be the vortices that proliferate at above the critical temperature. These are if you can define for each of these triangles a chirality variable, essentially the chirality variable that you use to characterize these guys is so you take a triangle and you construct this, and then you 2 by 3 and 1 by okay, I'm not sure, yeah. And with this chirality variable, you could see that this, okay, in this very simple configuration, this chirality variable does a loop around the singularity. So motivated by this topology behind the triangular antiferromagnetic system, we studied this extended Hamiltonian. So this is exchange in the usual way. And we have added this Dialoshinsky-Morilla term. So this Dialoshinsky-Morilla term points, the Dialoshinsky-Morilla vector points in the directions of the bonds. So in this way, okay? And so if you put together the exchange interaction with so you see this is pretty similar to what gave rise to skyrmion lattices in the square lattice case. I mean, in the structure that there is no out-of-plane component, although it could be, but we will not change these issues here. And the magnetic field. And the interesting thing is that one, at first, strange-looking state shows up, but I will show you that it's not so strange, okay? So as I said here, we don't expect to have skyrmions, but rather Z2 vortices. So in principle, my guess is that this is a Z2 vortex lattice, but we haven't been able to prove it yet. So, but let me show you some structure of this system. So if you know that the triangular lattice is tripartite, so you can plot this. This is a snapshot from a Monte Carlo simulation. You can split and plot the spins of the snapshots per sublattice, and this is what you see. So each of the sublattices is exactly a skyrmion lattice of a standard ferromagnetic case, of those that Bogdanov and Jablonski predicted in 1989, if I'm not wrong, or the years. Okay, so this is the situation. So these bubbles here that you see, this kind of strange bubbles, each of these corresponds to one center of the skyrmions on each sublattice. So if you have, let's say, in this lattice 10 skyrmions, so here you will have 30 of these bubbles, okay? So this is, maybe I should say, what is my German? I'm okay with time? Okay. 10? Okay, thanks. So what I was saying is that these are different from what one would call antiferromagnetic skyrmion, because an antiferromagnetic skyrmion is something like this. So it's a skyrmion on top of an antiferromagnetic background, okay? So that's why we cannot call the previous one antiferromagnetic skyrmion. So it's a kind of combination of skyrmions of three sublattices. So it's a kind of intertwined three sublattices of skyrmions that gives rise to this state. Okay, so antiferromagnetic skyrmions exist in bipartite lattices, and they look like this. So you see it's like a skyrmion, but also flips like an AF system. And so we started to look at the, so this is, maybe I will jump to the complete phase diagram, and then I will go back to some details. So the complete phase diagram from Monte Carlo, and later on with a continuum field theory description, looks like this. So here you have temperature, and here magnetic field. So at first, when the magnetic field is small, you get a spiral. But you get a funny spiral because this is triangular lattice, tripartite, and if you look per sublattice, each sublattice is a spiral, okay? Then if you go up in magnetic field, you get this phase here on the very right. But if you look at it per sublattice, is what I have shown you before. And here there is an intermediate region that we are still not able to completely characterize, or we can characterize, but we don't know how to characterize the transition, if there is any. So essentially, we called at the time a vortex phase. Why? Because here you see code colors. I didn't say, but maybe it was so obvious. So red is pointing, let's say, out, and blue inside the blackboard. So here the skyrmions have died. So here there is no skyrmion number per sublattice, okay? But there is still some structure. And so in order to characterize this evolution with the magnetic field, then I go back. Let me show you here the different variables. So first, the blue curve. The blue curve is the number of skyrmions per sublattice. So you count here the number, this is for a given lattice size, for some parameters. And if you look at the skyrmion number, you get 0 for the spiral phase, that's normal. Then you have this first order phase transition to a non-zero skyrmion number per sublattice. And then this goes down. Of course, it goes down with steps because it's a finite size computation. So the skyrmion lattice has to adjust to the size you have. But if you study this with the larger sites, you see that this will go down smoothly. And also we have done this with some continuum description. And we compare this with the vortex number. So how do you compute the vortex number? So we have used, we have borrowed from Kawamura Miyashita this vorticity that essentially tells you, so this is the rotation matrices that rotate the chirality around a given loop. So, but here you have a lattice system. So how do you, okay, so you define the chiralities everywhere, and you start to see what you get when you do all the loops. Thank you. And these blue dots here shows you when you get something non-vanishing, so when you get a vorticity equal to 1, so that allows you, there are many because you can catch the vortex from different loops, okay? This is very technical, but believe me that this counts the number of vortices. You can take loops, taking 3 sides or 4 sides, and you get these 2 curves here. And essentially, at least in first approximation, it looks that you get, if you had 10 skyrmions per sublattice in this lattice, you get 30 vortices, this set of vortices. Okay, so essentially, this is understood. And if you look now, as I said, this is non-vanishing skyrmion number per sublattice that goes to 0. And if you look at the intermediate, sorry, got it wrong. So if you look here, it's clear that there are no skyrmions per sublattice. There's still some structure when you look at the vortex number. So here, vortex number is definitely non-vanishing. So there is a transition between these 2 phases. One phase where per sublattice you see skyrmions, and in the other you don't see them, but you always see vortices. So this is still under study. Okay, and let me briefly comment on the low energy effective action. So we made it in 2 different ways. So first way, we took each sublattice, and each sublattice behaves like a ferromagnet. So for each sublattice you get the Bogdanov-Jablonski effective theory, and now you have 3 of them coupled together by a term like this that will make you intertwine the the 3 skyrmion lattices to build up the vortex lattice. And we are working now on a second calculation that where we would like to describe the low energy effective action directly in terms of the SO3 matrices. But this, okay, we have the effective action, but still then it's a bit cumbersome, so we don't have results from there. But from this theory, we could reproduce a phase arm with some simple ansatz. So essentially you get, for each sublattice you have a skyrmion lattice, and you know how to approximate it by these triple Q states. And then you have one for one sublattice, another one just shifted with some period, another one shifted with another period, and then you put the 3, minimize the energy, and you get again the right intermediate phase. Okay, so that's all what I wanted to tell you. What we are interested now, we are studying coupling to fermions and transport, and now I am also interested in the appearance of some polarization in these systems, coupled to 1D wire. And then in transport on these systems, this is something I have mentioned before. This is one of the papers, well, this is an experimental paper, and this is a theoretical one where they have seen this charge 2 skyrmion lattice, okay? And I think I will, this is experimental, and I think I will conclude here. Thank you very much for your attention.